Okay, this is the lecture that is associated with chapters 3 and 4 on the deep earth structure and plate tectonics. And I'm going to go through this rather quickly, a little bit more faster than I would do it if I were giving it in class, but you can get the idea from what you see here. So this whole notion starts with the idea of continental drift, that the continents were once together and then they've been separated and drifted to the present positions. And this whole idea we owe to this fellow named Alfred Wegener. Now, look at the title of that book, The Origins of Continents and Oceans. So this is how we got our modern oceans. A couple things to look at. So map of the Earth today at the bottom, and then as you go back in time more and more millions of years ago, you can see that the positions of the continents change, and therefore the positions of the oceans change. Look especially at the Atlantic Ocean. So if you go all the way back 200 million years ago, the Atlantic didn't exist. It was just one large landmass and then one large ocean. And as these different continents split apart and move apart, you created the ocean basins today. And I say the Atlantic because that's the one that's easiest to explain these concepts. A couple of important things. The large landmass is called Pangaea. The southern part is Gondwanaland. And Wegener did have large amounts of evidence, principally evidence from the continents. So if you looked at the different continents around the southern hemisphere, you saw the similar package of rocks in the similar order. And he reasoned that the only way that this could happen is if the continents were all together and then separated to where they are. He also looked at the fit of the continents, sort of the jigsaw puzzle fit. And there's a couple of figures there showing that, yes, indeed, you can fit the different continents together by closing various ocean basins. The especially good fit is between Africa and South America. Just another view of the same thing, this time emphasizing places where we have evidence of ancient glacial rocks. And you can see if these continents are together, they form a coherent bullseye pattern. If they're separated, as in the map of today, you have to imagine these glacial situations happening in all these different places, including some hot equatorial locations at the exact same time. A better look at the fit, sort of incorporating modern oceanographic technique here. Wegener just had maps to connect, but we can now connect sort of underwater bathymetry of the oceans, and the fit of, say, South America to Africa is far more precise. I am a paleontologist, so I love this evidence the most, but of course this doesn't have a lot to do with oceanography. It has to do with sort of anti-oceanographic creatures, land creatures and land plants spread out over all of these different continents. None of these things could cross big ocean basins, and so they are evidence that the ocean basins were closed. Some more pictures of these things, including this cute little Mesosaurus and then these Glossopteris ferns. The green pattern shows where they are found as fossils today. Again, you can't imagine these things crossing big ocean basins, so those ocean basins couldn't have existed. Well, for a whole bunch of reasons, continental drift was ignored until the 1960s, in which case it becomes what we know of as plate tectonics. That's the subject of your chapters 3 and 4. The basic principle is that the outermost layers of the Earth are hard and brittle. They are broken into pieces that we call plates, and below those outermost layers we have hot flowing material from mantle convection that's constantly moving this. So it's not necessarily the continents that are moving like Wegener thought. It is instead just chunks of continents and ocean basin areas moving around the globe. How do we get there? Well, the first step is seafloor spreading. Sonar, so the upper picture in the upper right there is a little ship sending down a sonar signal, one of those beeps. It travels through the water, hits the bottom, and comes back up. And the travel time gives us an estimate of the topography or the underwater bathymetry there. So if you have a giant mountain there, the signal only goes down a short way, then bounces up. If you have a big valley, comes this way. And what it revealed was in the map below, this is the classic National Geographic map where the continents are sitting there, the water of the oceans has been drained, and it revealed to us that the ocean bottoms are not just flat, featureless plains. They have the longest mountain chains on planet Earth, the highest mountains, the deepest canyons. Anything that you can have on the continents, the oceans have bigger and better. Especially notable are the central portions of the basins, which have these giant mountain ranges. Those mountain ranges then had volcanoes and earthquakes. Heat is rising here and spreading apart the ocean basins. Next, we have to look at the Earth interior, and this comes from the whole science of seismology, or the travel of shock waves through the Earth. This came along also sort of in the 40s to the 60s, and we revealed that the Earth isn't just a homogeneous ball. We have many different layers that have distinct chemical and physical properties. Going to become important for movement of plates. Just a quick picture of shock waves moving through the Earth. This is the type of data we get. Oops. Go back to this. And in this picture here, the uppermost area where the star is, you see that at the North Pole. An earthquake occurs here, and that sends shock waves through the Earth, and they travel at different speeds if there are different layers made of different chemistries and having different physical properties. Another image of this effect, and you see the little sort of stick figure people around the globe. An earthquake here happens on the extreme left part at the equator, and then the blue and pink lines are this different wave types. Don't worry about that. Traveling through the Earth, and they reach these different places or don't reach them at different speeds. If we set up seismographs, these devices that measure these waves around the globe, then we can find out where the earthquakes happen, all the stuff that's good about earthquake prediction technologies, but it also, again, helped us reveal these inner layers of the Earth. Like this, every textbook in geology around the world has some picture like this, a slice of the Earth showing the different large layers, and then at the outermost part here, the more complexity of these other layers. So let's look at those. There is first continental crust. We live on it, and there's its primary composition, its density. So if you imagine a perfect little sugar cube sized rock of continent, it would weigh 2.7 grams. Notice the thickness is variable, and this is mostly brittle. It breaks if you exert a force on it. We live on the continents, but this is an oceanography class, so this is a particularly important slide. Here, the sea floor, the crust, is made of mostly basalt. Its density, notice, is just a little bit higher, meaning it's heavier and it has sunk lower. That is why the ocean basins are lower. They are holes in the ground because the floor is heavier and it has sunk lower. Going a little deeper, the mantle. The mantle's this huge area. Notice it's over almost 3,000 kilometers thick, and again, the density increases. And here, the deformation is ductile, meaning if you exert a force on it, it doesn't break, it bends. So the crusts and the uppermost part of the mantle are brittle. They break. You exert a force on them, they break. Below that, the Earth is ductile. You exert a force on it and it flows. Below that again, the outer core, and you reach an area that's iron and nickel. The density is much higher, and we think it is essentially permanently a liquid. Go a little deeper, the inner core and the density is even higher. Do you have to memorize all those numbers? No, but you do have to remember that the density goes from very light, where we are on the continents, and then it increases into the oceanic crust, into the mantle, to the outer core and the inner core. Now think about it. This makes sense. The heaviest stuff is at the bottom, and it gets lighter and lighter as you go up. So at some point when the Earth was forming, all of this matter was sort of bombarding us. The Earth was aggregating together, and slowly over time, the heaviest material sinks, the lightest material, including ocean water, rises. Another way to divide up the Earth is by looking at the lithosphere. This is the two crusts plus the upper mantle, and the key point here is that this is brittle. This outer part here in this sort of gray and brown color, it breaks. When it breaks, it's going to make the plates. Below that is the asthenosphere. This is the upper, not the uppermost, but an upper part of the mantle. And here, heat rises, and this we think is kind of a half solid, half liquid, slushy mixture. So think about it. Solid material sitting on a slushy mixture. It's just like your car in the wintertime on the highway. This solid material can slip and slide over this lower friction material here. All right, go back to tectonics. Another evidence bit or data set that we've seen from this is that if you look at the global distribution of earthquakes, they are not random. They are very segregated into these linear features around the globe, which mark as well those mid-ocean ridges, those places where high heat flow exists. The distribution of earthquakes, same thing, seismic events, earthquakes. Every dot here represents a single earthquake. The different colors represent different sizes. Regardless, though, notice instead of outlining the continents that we know them, and they're sort of beaches, coastlines, they break apart different chunks. So for instance, this one I'm sort of looking at now, there's Africa, the continent, but it is part of this other larger chunk that includes parts of the Atlantic Ocean and parts of the Indian Ocean. What's moving these things? Well, the simple answer is mantle convection. The core is extremely hot. Remember, the outer core is liquid. The inner core would be liquid, but the pressures are so high, and heat is flowing upward. So hot things rise anywhere. When you boil water on a stove, the bottom surface is hot, and it heats up the hot material at the bottom where it's touching the flame, or your gas burner, or your gas or electric burner makes it rise. Same thing here. Heat source in the center makes it rise. All these little arrows are showing the motion of heat upward through the earth. It rises up here where we have these broken pieces, and here they're labeled as there's Africa, South America, Eurasia, the various oceans, and that's what's forcing things around. If we look at a map of the earth, not of the continents, the things that we sort of associate with the map of the earth, but instead the edges of these plates where we have earthquakes and volcanoes marking it, you have larger chunks. They're in different colors here. So for instance, here's the South American continent, but this gray pattern is what we call the South American plate. It includes the continent, but half of this Atlantic Ocean. Same thing with North America. We live on the North American plate, right about center here in this green area, but that North American plate doesn't end at the beach. It goes out halfway into the Atlantic Ocean here. Includes parts of Mexico, kind of butts up against a completely different plate here in the Pacific in these yellow color. Very important part here now, divergent boundaries. This is what makes ocean basins. We say that this is created by tension stress, that's the pulling apart of the earth. This makes seafloor spreading, and the key point geologically, when you go to these places, there are extensive volcanoes spewing out the rock type we call basalt. Lots and lots of earthquakes and very shallow. This is where we make those mid-ocean ridges. The next few slides just show sort of a standard set of this. Anytime you see arrows pointing apart in a geological figure, like these lavender arrows in the lower right, or just these simple black lines up here, that means those are two parts of the earth that are literally separating or diverging from each other. That occurs where this hot material from the mantle comes up, breaks the earth, and pushes things laterally. I like this slide especially because you see the divergent arrows, these lavender arrows in all of them, but you can see the rising heat, this hot orange area, it breaks the earth. It starts separating it. It separates it more, it separates it more. And folks, here's how you make ocean basins. The largest ocean basins on planet Earth, the Pacific, the Atlantic, were made by a crack that first formed in land somewhere. Ultimately, water flows in, moves aside, and the ocean basins grow and grow. There is a small little video for you to watch on the rates of plate motion, and they talk about this as being the rate that your fingernails grow or the rate that your hair grows. It's, yeah, that's, if you think about it, yeah, you don't cut your hair, you don't clip your nails, they grow, but you don't see it. You see the after effects much later. The rate at which this occurs is a few inches a year. And so if we have geologic time, millions of years, think about it, 5 inches a year times 10 million years. These small cracks can grow into larger and larger basins. Look at this map of the seafloor again, and there are those mid-ocean ridges going here. These are the places where it is separating by that several inches per year. And if we zoom in particular in this area of the Red Sea, notice this mid-ocean ridge comes down the Atlantic, whips around Africa, comes up through the Indian Ocean, and zip, goes over here between Africa and Saudi Arabia. There's Africa and Saudi Arabia. The Red Sea is right there. That is a spreading area. Looking at it from satellite view, you can see this, there's pesky clouds in the way, but there's the two land areas, Africa and Saudi Arabia, the spreading Red Sea. Zoom in with a satellite photo. Here's the upper area. On the left side is Egypt. On the sort of upper side is the Mediterranean Sea. Israel is in the sort of upper right, but the bright blue area that sort of comes up from the bottom and makes this bunny ear shape, that's the Red Sea. And there's a divergent boundary there. It is spreading apart. It is slowly pushing Africa to the left and Saudi Arabia to the right. It is spreading. If we go to this sort of bunny ear off to the extreme right, that's another little split, a little spreading area there. And zoom in on the coast. So if you're standing on the coast and looking at it, you can see the mountains in the distance. They are black. That is that basaltic rock. That's first bit of evidence that there's a divergent boundary here. And then you can see the angles of these mountains. They're sort of angled in on both sides down this center area. This area is breaking because of plate tectonics making mantle convection rise here. The heat cracks the earth, it breaks, and it moves. The right side of the world continues off to the right, the left side continues off to the left. What's some other bits of evidence that proves this? Well, paleomagnetism. There's a nice section to read in chapter 3 about the Earth's magnetic field and how this helps us prove seafloor spreading and plate tectonics. Go ahead and review this in the reading. I'm not going to spend a large amount of time talking about it here. Suffice to say, the Earth has a magnetic field. We expect our magnets to point to the North Pole today. That's what these sort of arrows pointing, sort of emanating from the South Pole, entering the Earth at the North Pole are here, but the Earth in the past has had a reversal. We don't know why it occurs. We think it has to do with how the motion of fluids in the core, these iron and nickel-rich fluids moving, make this field, but why it switches, we don't know. Suffice it to say, if you have a magnetic field that's constantly switching and a divergent boundary that's constantly sort of spewing out this basaltic lava, which has tiny magnetic minerals in it, then the seafloor is going to reflect this. It's going to have little crystals that point to the north when the magnetic field is normal, and it points to the south when magnetic field is pointing the other way. In this diagram, all the brightly colored stripes are same age rocks pointing towards the north, and then the light blue, robin's egg blue rocks are reversed polar. And if you go right down the center where it says Rift Valley at Ridge Crest, notice if you go to the right, you have a pattern of rocks pointing north, pointing south, pointing north, pointing south, pointing north, pointing south. If we age date those rocks, and we don't talk about that in this class too much, but if you age date those rocks, they get progressively older, away from the spreading center. That confirms spreading and plate tectonics. But then the pattern on the right side is exactly the same as the pattern on the left side. Again, confirming seafloor spreading and therefore divergent plate tectonics. Relevant facts here, this kind of thing. You just got to know this, folks. Magnetic reversals. Here's sort of we always have these nice cartoons of the beautiful pattern going from South Pole to North Pole, but clearly here's a map of the magnetic field lines today. There's a lot of complexity there. At some point in the past, they switch, and then these patterns would be reversed. Again, we don't know why. It just works. Again, this is a key slide just summarizing everything I just said. If you look at this here, the symmetries across mid-ocean ridges. So these sort of magnetic anomalies, they're mapped as a line here, sort of, and then as sort of tiger stripes in the picture. Point north, point south, point north, point south, and then a mirrored pattern or symmetry across this boundary. Well, that's what's shown over here in this map here. This is sort of a picture of the globe, and divergent boundaries are shown here. Notice if you look real close, you can see the arrows pointing apart. All those things I talked about, tension, stress, basaltic volcanism, faulting, shallow focus, earthquakes, all that's true there. But the Earth doesn't just keep blowing up like a balloon. You have to have other places where the oceans get destroyed. Now, if you think about it in bigger mantle terms, you've got rising heat at these divergent boundaries, but then it circles around and plunges at these other places where sort of indirectly you can see the arrows point together. We call those the convergent boundaries, and really, that yes, it's important, but all I want you to remember here is that for a lot of these things, this is the opposite of the divergent boundaries. It's an oceanography class. You need to memorize divergent boundary processes more. But convergent boundaries, the opposite. It is compression stress, not tension. Yes, there's volcanoes there, but they spew out a different chemistry of rock. And yes, there are earthquakes there, but instead of just having shallow ones, they're shallow, moderate, deep, deepest quakes. Key point for us in this class for oceanography is that this creates subduction zones with the deep ocean trenches, the deepest part of the Earth's oceans. So in cartoon form here, you see the two arrows pointing together. this oceanic crust is being forced towards this continental area. The continents are light. They're going to stay light. They're bobbing on the earth like corks in the water, or like fishing lure bobbers on the water. This heavy oceanic crust is being pushed to this lighter oceanic crust, and it goes down. The heavier material will always go down. When it does it, it creates this place called a subduction zone, which has deep, deep, deep ocean trenches, the deepest parts of the ocean. Very important stuff. Not necessarily something I'm going to make you know a lot about for this class, but realize this is where the ocean basins get destroyed. A classic example would be off the west coast of South America. This slide summarizes the three boundary types. The upper part, divergent, making oceans, put stars by it. This is the big important one for us. Middle one, convergent boundary. This is where we close ocean basins. Don't worry about this bottom one, the transform one. Distribution of volcanoes, just another bit of evidence to confirm this, that volcanoes aren't scattered randomly. They're associated with different boundary types. Again, map of the Earth. If you look around here, anywhere one color meets another one, that is a plate boundary, a boundary where one of these big chunks of broken, hard, brittle material is meeting another chunk of broken, hard, brittle material. And we ask ourselves then, are these two plates coming together, converging, or are they separating, diverging? Where they separate, we're making ocean basins. Here's a picture of this. These last few slides are just different confirmation bits of evidence that confirm plate tectonics. I'm going to have you go ahead and read in the text about hotspots, with Hawaii as a primary example of this, that if the hard brittle plates are moving over a hot spot, a place where this hot material is always moving, you will create a stripe of volcanic islands that progressively get older and older away from the hot spot. And we have that. We even have these things on land. If you go to Yellowstone National Park, I know a lot of you have been there. That is the site of a hot spot, but the track of it goes across through Idaho and into Nevada and ultimately California. And this hot spot gets older and older the farther away you go, because North America is riding over this continual spot here. There are a lot of other things in the oceans besides these mid-ocean ridges. Look at the other side of the Pacific. All these little sort of mountainous type areas, collectively they are called oceanic plateaus, and some of them are so thick that they will not get subducted. They will not just get flushed down the subduction zone like the rest of that oceanic crust. Instead, they get scraped off. It's called accretion. So in this figure right here, Australia is in the lower right. The rest of Asia would be off the slide in the upper left, but Australia is slowly but surely plowing into Asia, and all of these sort of plateaus, ocean areas, are ultimately going to not get flushed down under Asia, subducted, but added to it. Asia is going to get bigger. Think of it in oceanographic terms. Here, Australia's in the lower left. Asia would be off to the upper left here, and these things that you've probably never heard of before, the Magellan Rise, the Manihiki Rise, the Ontong Java Plateau, these are these thick chunks of oceanic plates that they're all on their way up towards these subduction zones of Asia. They are too fat to go down, so what's going to happen, these purple polygons, these giant landmass sizes, are going to be scrunched up and added to Asia. They're going to be accreted to it. We call these things terrains. They're an interesting little side bit. Today they're on the land. You can walk on them, But the beautiful part about it is it's a place where you can walk on what once was an ocean floor. The second most important part about it is that sometimes these things are very, very exotic. They will contain fossils and rock types that maybe they first formed in the southern hemisphere many hundreds of millions of years ago. Plate tectonics has pushed them completely across an ocean basin, and now they've been added to, pushed up onto a landmass somewhere. And I showed in that previous slide, I showed that Asia's going to get bigger. Well, North America has already gone through this process. And in fact, this whole thing hasn't been known since the 80s, but look at this map here. This is North America as you know it, and all of these irregular little polygons with these names here, these are different chunks of ocean material that were added to, they were accreted to North America. North America itself in the past was only as big as this dark brown area. All of these things are oceanic plateaus, island arcs, chunks of the ocean bottom that have been pushed up and added. So all of California, all of Oregon, all of Washington, huge parts of Alaska, Nevada, etc., they're on land today. You can go there, but they were once ocean basins. So you can do oceanography both in a sort of modern, in the water sense, but in an ancient, on the land sense. And this is everywhere. I always throw this in here just because I've done some research in Scotland, but all of Scotland is consisting of several terrains, chunks of land that were once ocean pieces, or in the case of some of these northern highlands and Hebrides terrains, they were once chunks of North America. So in California, we have pieces of California made in China. In Scotland, we have pieces of Scotland made in North America. Anyway, this is a nice review of plate tectonics. Hope you enjoyed it.